concept of Gaussian mixture model. So as we know, Gaussian mixture model will be the one that, can solve some of the some of the k-means problem where it will make like a solved decision and it will perform clustering based on density estimation using probabilistic model. Another thing about Gaussian mixture model that I said it can be robust to noise is the fact that you can look at this example. For k-mean, right? If you have the points that is far away, if it still closest to that centroid, that points will be part of the clustering. But it cannot tell whether or not this point is more important than that point. So there's no weight whatsoever. It's just giving you the cluster that these points belong to. Meanwhile, Gaussian mixture model, even though I can highlight the cluster, but in fact, this highlight came from the probabilistic density. Actually, if you look closer, you will see that there are some blurred line here. Actually, I kind of plot the peak of the density versus, so it's a contour plot. And actually, this point, let's say here, we have much lower weight to the red cluster when compared to if you look at this one that doesn't have any weight. It just tells you it belongs to the red one. So in Gaussian mixture model, because it uses probabilistic model, it can really give you the probability of how it's like what is the chance that this point belongs to this cluster, and as well as what is the probability of this point. So you can compute the PDF and the conditional distribution, the joint distribution, and that can happen because we assume a probabilistic model to these data points, and that is kind of one of the features of this Gaussian mixture model. So let's look at what is exactly Gaussian mixture model before we go over this. By the way, I think this sentence that I wrote, that GMM cannot solve this problem, is kind of wrong because it can handle noise, but it just cannot identify noise. Or you may have to identify it using some probability value that you can derive from Gaussian mixture model. So somehow Gaussian mixture model can give you enough information to identify the noise, but it just doesn't give you right away. Unlike DB-scan can identify the noise right away. So that's why a lot of people find that DB-scan is actually simple and just straight to the point. Meanwhile, for Gaussian mixture model, you need some post-processing to understand the data. That's why it's actually good for if you want to analyze your data further. Yes. Yeah, so it sees noise as a variance of your data, like it's just part of the data that has lower chance, something like that. Okay, so what is it? Okay, before this hard stuff, let's just go to the concept of the GMM. Okay, so please don't be scared by the notation. I understand it will look really scary sometimes, but just be with me. Okay, so as I mentioned before, Gaussian mixture model will use some probability to identify the cluster of the data. So in fact, let's skip forward a little bit and use this cat picture. Okay. Let's just look at the inference phase of the Gaussian mixture model. The inference phase of Gaussian mixture model would involve with that you have like a probability value, and in this case we denote it as tau jk, where j being like an index sample of this xj, and k is the like an integer value that is used to identify the class. As we know, Gaussian mixture model will assume the number of clusters, right? So let's say this big K is the maximum number of clusters that we think there are. This small k will be, those clusters indexes. And x here could be our input samples. The subscript j just means that this is like the sample index. Let's say if j equal to 1, it probably means your first sample. Okay, so this tau jk is actually equivalent to this probability of being in that cluster given input sample. Or on the other words, what is the probability that that the sample J is in cluster K? Okay, I'll just write it better. So this is like a probability that sample J is in cluster K. And the reason that we use prop of K given, prop of the cluster given samples J is because if you think about the scenario where you are given a testing sample, like you have a data sample and you want to know which cluster that sample should belong to. So naturally, given that samples, you want to infer the cluster. So that's why you use this conditional probability. So given xj, what is the prop of sat equal to particular k, where k could range from 1 up until k. And you find the one that you find a cluster that gives you the highest probability. And if you find which cluster gives you the highest probability, probably that means that xj should belong to that cluster. And this is, once you have this tau jk, you can find a cluster. So that means your probabilistic model, that Gaussian mixture model, would be like a function that somehow you can derive this tau jk. And actually, all right, that's okay. I'll just go back to then how shall we get this Gaussian mixture model, and how does this Gaussian mixture model become tau jk? Okay. Let's keep in mind that tau jk is the probability of sat given x, or probability of belong to a cluster given input sample. Okay, so this is the Gaussian mixture model. Gaussian mixture model is defined by this equation. And the one below here is how can you derive the tau jk if you were given a Gaussian mixture model. So if you can compute this Gaussian mixture model, it means first, you receive this xj. Second, you know what is the function of that probability of x given sat and probability of x here. Therefore, you can use Bayes' rule to derive probability of sat given x. And you know what is that pi k. But I will give you, not hint, but in fact, definition of these parameters. Firstly, in Gaussian mixture model, as I mentioned before, that this equation is actually the Gaussian mixture model. Gaussian mixture model is the weighted sum of Gaussian distribution. And tau k here is a weight, usually being a value between 0 and 1. So you can think of it as like a probability that this pop of x given sat happen. Actually, if you think about probabilistic interpretation, interpretation that you know can get the pop of x here. This tau k will be equivalent to the probability of z equal to k. Maybe I should write. This is tau k. When tau k is, so not tau k, pi k. When pi k is probability of z equal to k, and you have probability of x given z, you can use some base rules to derive further that probability of z, probability of x given z here. These two multiply will become the joint probability of xz. Am I right? Okay, I will just put it in the same. Am I right? This base rule. Base rule will be defined by this. I just swap that to that. And that means that this, whatever this is actually this one, where this pi k will be pop of z equal to k. And since we know that k is like a random variable, sorry, not k, the z is a random variable that can take value from k equal to 1 up to k equal to big K. So that means when you do the summation, you know, when you do the summation of pop of x joint of x and z equal to 1 up until big K, this is actually marginalization, right? You can think of this as equivalent to if you were, if it's in the continuous space, then that is, it's actually equivalent. It's just that in this case, if you write it like this, that means your z is a random variable in continuous space. But in this case, because we were using z as like a probability of, it's a random variable of being in a cluster, or probability of that cluster. So that means that is going to take integer value, and in this case you have, that integer is the cluster ID, which start from 1 up until big K. So when you do it like this is marginalization. So that's why you get prob of x here. Sorry. Okay, that's why you get prob of x here. That's because you marginalize it out. Marginalize. And once you marginalize and you get prob of x, or maybe xj, we know that this is a Gaussian model. But if we want to get the probability of that cluster given input x, that means we can again use something like previously. So this is equivalent to one another, right? This is joint prob of xz divided by prob of x, then it becomes prob of z given x. That is your tau. And all the things here that you see are just base rule. Actually, I forgot to say, so which part is Gaussian? The part that is actually a Gaussian distribution is prob of x given z. This is this part. this is the part where the Gaussian assumption is made. Okay. So in Gaussian mixture model, we will assume that this, the PDF of this one is a Gaussian with means equal to mu k and sigma k, variance sigma k. And you probably have this, I'm not sure. It's like there's a question of like why you have subscript k here. Actually, if you think about that, it's a pop-up X of that cluster, we probably want to assume that any samples that are in the same cluster, they share the same distribution, right? So if they share the same distribution, they will share the same parameters. That is the mu and sigma for Gaussian distribution. So in this case, every xj that j is in cluster K will have the Gaussian distribution where the mean is mu k and the variance is sigma k. Okay, so that's where the Gaussian mixture came from. Actually, on the other words, the Gaussian mixture, you can think of it like it's a mixture of the Gaussian, but it's a mixture as in it's like a weight sum. You can think of it this way as well. And all the rest of the interpretation came from Bayesian's rule. Bayes' rule, sorry. Yeah. And the thing is, another thing that you should keep in mind, in some textbook, tau jk, if you use like a direct interpretation, this is what you get. But when you actually have to compute it in coding, some people will compute tau jk. Sorry, I'm not sure how to write tau. Some people will compute tau jk by approximated with the joint distribution. Just keep in mind that this can happen. Okay. And as we have, let's say, big K number of clusters, that means you have to have big K pair of mu k and sigma k, as well as the pi k. And that's the reason why in the next slide, as you will see, the GMM would involve these set of parameters. So that means you have 1 pi k, 1 mu k, 1 sigma k for each individual Gaussian distribution. And when you sum it together, that becomes mixture of Gaussian model. And here, this denotation simply means that, it's like a set that is ranging from k equal to 1 to k equal to the big K. That's the parameters. And yes, with these parameters, you can compute the joint distribution, the likelihood distribution, the posterior, that is this one, or the marginalized distribution. So with these parameters, you can compute many things from it. And once you can compute all of these, that means you can calculate the value for tau jk. So the idea of Gaussian mixture model, when you use it for the clustering, is actually doing the following. So it will start off with initializing some value to the model parameters. In this case, from k equal to 1 up to k, this entire set. They will randomize something. Just like when you randomize the cluster in the K-mean clustering. After that, you will compute this tau jk because we could just do it. And don't forget the fact that whatever tau jk here is driven by these model parameters as well as your input samples. Once you get the tau jk, this tau jk could be used to find your cluster. That means it's like a medium, just like when you use the Euclidean distance to identify which cluster that this sample should belong to. In this case, you get a tau jk. But with this new tau jk, you can then use it to re-estimate these model parameters. And you would do this through what we call a maximum likelihood estimation. And usually, but I haven't provided you the detail of how to compute it. Please don't worry. This is just to give you an idea. And once you iterate between the two steps, like you compute two, then once you have this updated version of the parameters, you then recompute this tau jk again. This tau jk can be computed using these parameters as well as the input sample. And then you use this tau jk to then re-optimize for these parameters again. You will keep doing this until you get a very steady tau jk. So that's what happened in this algorithm. So you can think of tau jk as a centroid if you want to compare this to the k-mean. And in fact, k-mean can be compared to this in a sense that if we were to fix all the parameters except mu stat k. For example, if you fix this pi k to 1 and maybe sigma to, like a diagonal, then all the rest of your parameters would be this mu, that is the centroid of the Gaussian model. And of course, the parameters that you would get associated with this would be a probability that is proportional to that least square. I'm not sure. If you think about this exponential of x minus mu k, this term. And actually this term is the Euclideans. So if you only have mu k, the mu k left, that means that your tau jk would be kind of proportional to these terms. So in some way, sometimes people would say that, GMM is like a soft version of the k-mean. And it's actually like a k-mean where you further enable the algorithm to estimate for the variance and the pi k. But if you don't want to estimate for variance of pi k, then it returns back to the k-mean estimation. Okay, shall we move on? And actually below here are the example of what it looks like. So as you can see here, initially, you only get like a set of parameters, which doesn't well represent your data. But as you recompute the tau and update with your data samples, your hyperparameters will start to morph to your data samples. That is the circular shape and the oval shape here are actually representing your variance. And the center of the cluster is your mean. So yes, it's kind of look like you are, if you think about this in a sense of k-mean algorithm, it's actually quite similar. But the difference is that in Gaussian mixture model, the parameters for sigma or variance are actually keep being re-estimated to the point that it fits with your data sample. And we will talk about this in the second part, like how did we actually update these parameters. Anyway, so this is just to give you a rough idea. Another thing before we take a break, that is, so, to be kind of precise to what we're doing, not what we're doing, but it's like to be more precise about the random variable that we are using in our Gaussian mixture model. We know that we have x, right, being the random variable of our data samples. And we also have the Z here being the random variable of each cluster. And in fact, you should notice that one set, I mean, in this case, we have only two clusters where you have Z1 and Z2. And Z1 is linked to every random variable that is this data samples. Z2 is the same, like it's linked to every random variable that is data samples. That's kind of representing the fact that you can always calculate prof of xj given z equal to maybe k equal to 1, or prof of xj given z equal to 2, or you can do like prof of z equal to k given xj, where k could be, like 1 or 2, stuff like that. That is like to link how many random variables are there and how are they actually put together into this distribution. Because sometimes, but you will see in the second part, at this stage, the number of value that Z can take is much less than the number of samples xj. For example, you can have xj, from 1 up until, let's say, maybe 100,000. But you may have only 3 clusters, right? So if that was the case, that means the number of value that ZK can take is incredibly less. Yes, so that's something that you should keep in mind. But also keep in mind that, this xj, when we talk about prof of xj, especially this one, is actually the probability of your feature value. That means this one, xj, or whatever input feature is actually Rn. It's actually a big distribution. If this one is a Gaussian, it's going to be a very big Gaussian distribution. And x is continuous for each dimension. Just keep in mind for that. And yes, this prof of xj can be used to identify whether or not that xj is significant. Because if your value is kind of low and unrelated to anything, definitely the probability of these samples will be small. So it could be taken as noise. Yes. And what else about this graphical model? Graphical interpretation. The next thing that you have is pi. That is like the weight of each Gaussian. And also mu1, sigma 1, actually this one could be like a sigma 1 like this. It depends on how big is your how big is your x is. If your x is just a scalar, then you will be fine with having sigma 1 being just a scalar, because don't forget that this definition of mu and sigma is the one that we impose on prof of x given z. Right, so if x is scalar, using sigma is fine. But if x is high dimensional, then this sigma have to grow. Let's say if x is in Rn, then mu k will be a vector in Rn as well, and your sigma will grow to a matrix in Rn times n. This is the dimension of your input features. So this is something to keep in mind about what you're doing. But we wrote it this way, like, putting z, pi, and mu sigma together is just like telling you how the parameters are sharing. So yes, sometimes people call model like this like a plate model, which means you're trying to tell them, not exactly plate model, but it's like you're trying to tell them how these parameters are being shared across random variables in your setting. Actually, there's another way to write this as well. Sometimes you will see some probabilistic writing just like this. Like it's just notation, like you get sat being, like a sample that has distribution equal to pop of sat maybe equal to sat k, and there's pi k associate because this is the parameters of that probability. And then your x, xj of, if you talk about xj that came from that sat k, it's going to be this probability, right? And then actually there are some, in here I haven't add the Gaussian elements, but if I add the Gaussian elements, then that will be sat j sample from pop of x given like this. Like you can change it to this form as well. This is just to give you like an overall of the elements inside this. Yep. And we will talk about advantages, disadvantages, and then we'll take a break. So, yep. So advantages of the Gaussian mixture model, it can, let's say, model various shapes of the cluster depending on the assumption that is imposed on the covariance matrix. So yes, covariance matrix could be any. It could be, diagonal. It could be like an n times n matrix. Whatever you think that is suitable for your data. But generally, people normally use it as a diagonal because it's easier to implement. But yes, if it's a diagonal that share the same variance for all the diagonal elements, it may not be that different from the Gaussian mixture model, from the k-mean clustering, because k-mean would probably assume, everything equal because it's optimized based on the Euclidean distance. And yes, the second thing about Gaussian mixture model is that it has the probabilistic assignment, but it still has some kind of, disadvantages. It needs some predefined number of clusters. You already know that. It doesn't have function to identify noise, but it can be robust to noise. But the third thing that probably most concerned is the fact that it's quite computationally intensive, as we will see how intensive it is in the second part. But let's take a break for time being. Okay.